These are notes on the EvoDot activity, and some people have expressed that they wanted a little more guidance and a little definition of some of the terms we used, and so this is meant to accompany the EvoDot activity, and they assume that you've done the activity. So we're going to start with dot size is variable, heritable, and there's selective pressure. So variable means there are different sizes. So as you can see from my starting population here, there are red dots that are really big, there are black dots that are really small, and everything else kind of follows the spectrum and is in the middle. And then heritable means when I click on the reproduce button here, that the dot size will be inherited. So a red dot would give birth to another red dot. A black dot would give birth to another black dot. And there is selective pressure, means there's something from outside, namely me, that is controlling which dots get killed off, giving the size an advantage. And that's the one that I think a lot of people have been a little confused on, so we'll talk about that when we get there. But if this is my starting population, you can see I've got, this kind of distribution where I have the fewest number of black dots, and this actually ends up being kind of a bell curvy type of thing. That's random though. As you know, when you do the EvoDot activity, it's kind of random what you start with. And I'm not going to look at specific numbers. And in fact, I didn't time myself for 30 seconds. I simply killed off 25 dots each time, because that was something I could keep track of versus having to time myself. And so the numbers, the total numbers actually remain the same, but we want to look at what happens within the population. So remember, a population is all one species, meaning all these dots are the exact same species. There's just some variation within them. So I did pretty much the exact same thing you did, which was I killed off 25 dots, I let them reproduce, killed off 25 more, let them reproduce. I went through 3 generations. So at the end of 3 generations, this was my population. Okay? So as you can see, the number of black dots has increased a lot. So this was originally out of 13, and there's maybe 1, 2. I don't know that I killed any black dots. There's got to be more than 2, because otherwise there would be fewer. Oh, well, no, that might make sense. At any rate, as I said, I don't know that I killed any black dots, especially since I'm using the mouse on my laptop instead of an external mouse, and as you guys know, that's a lot harder. But you can see the black population is increased, the purple population is increased, even the blue population has increased when you look at this scale. This is out of 22, this is out of 13. The green population is decreasing. The yellow, orange, and red populations are gone. And so what we've seen is maintaining the same number in the population. We had 50 at the start and we have 50 now. We've really seen a shift in this population, and that's what we mean by change over time. Each individual dot didn't change, but the population as a whole shifted to favor those dots that were smaller, because they were harder for me to click on, and because small dots give birth to small dots. If there were a lot of small dots left over, then those would have reproduced and made more small dots. At the end of my first round, I don't know that there were any red ones left, and so there were no red ones to reproduce. And so that red large dot trait died out in that variation. Okay, so now let's look at the dot's size. That should be dot's size is variable, but it's not heritable. And so that means that, and there's still selective pressure, so I'm still able to kill off selectively. And so what that means is we still have all different sizes. And so this was right here, our original population, okay? And as you can see, remember before I said it looked like a bell curve, every time this program populates, it populates differently. So this one populated a little differently. This, though, is after one set of killing, but before I reproduced. Okay? And so notice, after I've killed 25 dots, and you can see here's 25, I again have no more yellow, red, or orange, just like we saw on the previous slide, because those are the ones I've killed off. But the key is here that dot size is not heritable, meaning it is not able to be inherited. And so a green dot doesn't necessarily give birth to a green dot. It may give birth to a red dot. And this is like any number of traits that are not heritable. So like language is not a heritable trait. An English-speaking person doesn't necessarily give birth to an English-speaking child, right? Language is something you have to learn. And so after 3 generations, and then I reproduced, this one was before I reproduced, after 3 generations and reproducing, so back up to the original 50, this original 50 is comparable to that original 50. If we compare these two charts, the starting population of 50 and the current population of 50, you'll see that there have been changes. There's less yellow. The blue and yellow populations have gone down. The orange and red have gone up. The green, purple, and purple have stayed about the same. Black's gone up a little, but there's no trend. There's nothing you can predict. It's possible that, that there just weren't as many blue and yellow births, and that's why they went down. There's no way you can talk about a real shift in this population. And this was after 3 generations. If I had done this 3 more times, I may have come up with something completely different. The other thing to notice is after this one set of killing, but before reproducing, there was no red, orange, and yellow. But because the trait's not heritable, so a blue dot could give birth to a red dot, at the end of the entire simulation, I do still have red, orange, and yellow, and in fact, I've got a lot more orange than I had originally. So the fact that, yes, I still killed off the slow ones, the large ones, because it's not heritable, then you could still give birth to ones even if you had killed them off before. So in order to find a shift in population, you need a trait that's actually heritable. So now this one, the dot size is heritable, but it's not variable. In other words, there's no variation within society. And so I have a starting population of 50 green dots, and I killed off 25 and I reproduced them. It's heritable, so green gives birth to green. So my ending population is 50 green dots. So you could think of this as, let's say, number of noses. We have 1 nose. So if something is killing off humans, let's make this less gory. Let's take cows, okay? Or what's something we hunt? Why am I drawing a blank here? Let's take deer, okay? And you're out hunting deer. Deer, similar to humans, have 1 nose, right? That's heritable. The deer have 1 nose because they inherited that trait of having 1 nose. But it's not variable. So every deer you kill off has 1 nose, and so that doesn't cause a shift in the number of noses in society. Then all the deer reproduce, and the ones that were left all had 1 nose, and they pass that on. So that's something that's heritable but not variable. And so in order to see, again, a shift in a population around a certain trait, around dot size, this might be different if something else were variable, but we're looking specifically around dot size. In order to see a shift in population around dot size, you need to have some variation in the dot size. And so then finally, the dot size is heritable, so you can inherit it, and it's variable, so there are different variations. We have big dots and we have small dots, but there's no selective pressure. In other words, what is causing the change from outside, almost you could call it like a competing factor, doesn't have anything to do with size. So let's think back to the deer, right? And let's say deer eye color. Now, my guess is that deer actually probably all have the same eye color. But let's say they don't, okay? And that's going to be heritable. It could also be variable. You could have different eye colors. But it's possible it has nothing to do with the rate at which they're hunted. That a deer with a lighter color eye is not at any sort of advantage compared to a deer with a darker color eye. So there's no selective pressure around eye color. Then the fact that it's heritable and variable also doesn't change the population any. So this was my starting population, and again, notice it's random. We have a completely different distribution than we had before. And after 3 generations, this was my ending population. So you'll notice there is no more yellow. That has died out given the amount we started with, and that yellow is a relatively large dot. That was killed off pretty early, but that doesn't necessarily cause a major shift in the population. You'll notice this is still a very similar distribution because things are being killed off randomly as far as dot size goes. This was the one that as you clicked, dots just disappeared, and it was random. And in fact, let's say you end up with a smaller population of something, then there's a lower chance that that's actually going to be the one that's killed off. Just think percentage-wise. If we look at this starting population, you know, the red and the black have maybe a, I don't know, 2 in 11 chance of being killed off, whereas the green has like a 10 in 11 chance of being killed off. And so it's more likely to get killed off, but then it's simply going to reproduce and you're going to get those greens back, and so it's going to maintain the approximate ratios that you had before because there's no selective pressure around that trait. And so in order to see a shift in population, we've now seen something needs to be heritable, able to be inherited. You need to see variation in that trait, and there needs to be selective pressure surrounding that trait. And so hopefully that kind of helps you bring all of the EvoDot stuff together. All right, have a good night.